I welcome you all to my YouTube channel Insight into Chemical Engineering. In this lecture series, we will solve the unsolved problem of a famous book, Stoichiometry and Process Calculations by K.V. Narayanan. These lectures are helpful for chemical engineering students because it is a core subject for chemical engineering branch. So during lecture, step-by-step solution will be provided. And in this lecture, exercise number 4.62 will be covered. Please like and subscribe for motivation. Problem number 4.62. In the nitric acid manufacturer, 100 meter cube per hour of ammonium at 290 Kelvin and 1 bar is mixed with air and passed over a catalyst in a converter, and the following reaction takes place. Further, the gases from the converters means whatever the gas that will come out from the converters are passed into an oxidizing tower where the oxidation completed according to the following reaction. So again the reaction is given for oxidizing tower, and further the gases that will come out of this oxidizing tower are passed into a cooling tower, and in cooling tower there is an absorption of NO2. So NO2 is absorbed in 50 kg per hour of water and forms nitric acid according to the reaction, and the overall reaction for the process is also given. Further, it is given that air supplied is 20% in excess of that required for complete oxidation of the ammonium to nitric acid and water. So here, as per this equation, because in this equation there is a complete oxidation of ammonium to nitric acid and water. So as per this equation, 20% excess air is used. So using this equation, we can find out the amount of air used. Further, the degree of completion of the reaction in the converter is 85%, and 90% of nitric oxide entering the oxidizing tower is converted to nitrogen peroxide. Assume that cooling tower exhaust gas contains no water vapor. So there is no water vapor. Whatever the gas that will come out of cooling tower, calculate the followings: the amount of air to be used in meter cube per hour at particular temperature and pressure, and the gases leaving the converter, and the amount in kg per hour, and the concentration in weight percentage of nitric acid produced. So in next slide, first we will try to understand the whole process. So we will write the whole process in the block diagram so that we can understand what is happening. So ammonium is available at 100 meter cube and 290 Kelvin and 1 bar. So this is the converter. So initially it is given that gas are entering into the converter. So ammonia is the entering gas as well as air, and the conditions at which ammonia is entering to converter is also given, that is 100 meter cube per hour, and temperature is 290 Kelvin, pressure is 1 bar. and what is the reaction that is going on inside the converter is also given. So ammonia is reacting with O2 and giving H2O and NO. Further, this leaving gas will enter into another tower. So this is the oxidizing tower. So leaving gas from converter are being passed to oxidizing tower. So in the oxidizing tower, the reaction between NO and O2 is happening. And further, the gases whichever will come out of this oxidizing tower are sent to cooling tower. And also in cooling tower, the water is coming at 50 kg per hour, and in the cooling tower NO2 is absorbed, and NO2 and H2O are reacting, they are giving HNO3 plus NO. And again the gas will leave the cooling tower, and overall reaction is also given, that is NH3 plus 2O2 gives HNO3 plus H2O. So this is the overall process. So part A, we need to find the amount of air to be used in meter cube per hour at 1 bar and 290 Kelvin. So here we have used the ammonia at 1 bar and 290 Kelvin. Corresponding to these conditions, we need to find the amount of air to be used. So we will use this equation because already in the problem it was given that excess air is used corresponding to the overall reaction. So for that, what we need the number of moles of NH3, because from this equation we can say that 1 mole of NH3 will require 2 moles of O2. So first we need the number of moles of ammonia. So for that, volume is given, that is 100 meter cube. Temperature is given and pressure is given. So using ideal gas equation, we can find out the number of moles of ammonia. So number of moles of ammonia equal to PV by RT. So pressure is 1 bar, volume is 100 meter cube, temperature is 290 Kelvin. So first convert this bar to SI unit, that is Pascal. So after putting all values, we will get the number of moles of ammonia, that is 4.147 kilomole. Now as per problem, it is given that air supplied is 20% in excess that required for complete oxidation of ammonium to nitric acid and water. So this is the equation. So first we can find out the required amount of O2 for the complete oxidation. Then we can see that 20% excess air is used. So corresponding to that, we can find out the total amount of air used. So in the equation, we can write 1 mole of NH3 requires 2 mole of O2, and the available mole of NH3 is 4.147. So 4.147 kilomole of NH3 will require 8.294 kilomole of O2. So this is the required amount of O2. So we need to find the excess O2. So 20% excess O2 is used. So this is the required amount. So 20% of required amount will be equal to 8.294 into 20 by 100. So this is the excess air that is used. So it will come out as 1.659 kilomole. So this is the theoretically required oxygen and this one is the excess oxygen. So total O2 used will be equal to theoretically required plus excess. So total oxygen supplied will be equal to 8.294 plus 1.659. So it will come out as 9.953. So we have estimated the total oxygen supplied. Now from this we can find out the air supplied. So total air supplied can be estimated. So we know that 21% of air gives the moles of oxygen. So in the previous slide we have seen that the total moles of O2 supplied is 9.953. So 20% of air should be equal to the amount of oxygen. So from this equation we can find out the moles of air. So air supplied will be equal to 47.395 kilomole. So further we can write the moles of N2. So moles of N2 will be equal to 79% of air. So we can find out the moles of nitrogen. So further we can find out the volume of air using ideal gas equation. So after putting all values we will get 1142.72 meter cube. So this is the volume that we have to calculate. Now part B, the amount of gases leaving the converter in meter cube at 0.95 bar and 1000 Kelvin. So first we will see what is the reaction across the converter. So this is the converter and in converter NH3 and O2 are reacting, they are giving H2O and NO. And we also know the composition of entering gases. So here the ammonia is entering and air is entering. So we have estimated the moles of oxygen and moles of nitrogen. So these are the moles of nitrogens and here we have used the moles of oxygen. So these are the inlet conditions for converter. So after this the gases will leave the converter and we need to find the composition of these leaving gases, and further it is mentioned that these gases are living at particular pressure and temperature. And it is given that reaction in converter is not 100%. So the degree of completion is 85%. It means whatever the amount of ammonium is there, so some amount of ammonia will get converted and some amount of ammonia will come out as unconverted. So we can write the moles of NH3 reacted will be equal to 85%. So it will come out as 3.525 kilomole. So only this much mole will react. So remaining moles will come out as unreacted in the living gas. So we can write moles of ammonia unreacted equal to 15%. Or we can also calculate the total moles is 4.147 and reacted mole is 3.525. So by taking their difference, we can also find out the unreacted moles of ammonia. Now we can also find out the moles of O2 reacted and moles of O2 unreacted, and N2 will act as inert. So whatever amount of N2 is there, the same amount of N2 will come out in the living gas. Now from this reaction we can say that 4 moles of NH3 requires 5 mole of O2 and 3.52 kilomole of NH3 are reacting. So corresponding to these moles we can find out the amount of O2 required, or we can say reacted. So 1 mole of NH3 will require 5 by 4 and 3.525 kilomole of ammonia will require 4.406 kilomole of oxygen, and this is the available amount of oxygen. So this much will get reacted and the remaining amount of O2 will come out as unreacted. So we can write moles of O2 reacted equal to 4.406 and moles of O2 unreacted will be equal to available moles of N2 minus a reacted mole. So it will come out as 5.547. Further, we need to estimate the amount of water and amount of NO, because these two components will also come out in the living gas. So again we will rewrite the equation. Now we can write 4 moles of NH3 produces 6 mole of H2O. Now corresponding to reacted moles of NH3, we need to estimate the amount of H2O produced and amount of NO produced. So we can write 1 mole of NH3 produces 6 by 4 mole of H2O and 3.525 is the reacted moles of NH3. So this much mole will produce 5.287 kilomole of water. So in the same way we need to find the moles of NO produced. So 4 mole of NH3 produces 4 mole of NO. So 3.525 mole will produce the same moles of NO. So we can write the composition of gases leaving the converter are unreacted ammonium and unreacted O2 and unreacted nitrogen, because nitrogen is inert, and further water is produced and NO is produced. So these are the composition of living gases. So we can find out the total moles leaving the converter. So we can add up all components. So we will get 52.423 kilomole. So as per problem, we need to estimate the amount of gases leaving the converter in meter cube per hour at given pressure and temperature. So number of moles of total gas leaving the converter is known, pressure is given, temperature is given. So using ideal gas equation, we can find out the volume of gases leaving. So volume of gases leaving the converter equal to nRT by P. So here N is the total moles of gas leaving converter, that is 52.423, and further temperature and pressure conditions are given. So we need to convert this bar to Pascal. So after simplification we will get 4587.84 meter cube. Now we will go to the next step, that is oxidizing tower. So whatever gas that will come out of the previous tower will enter into the oxidizing tower. And just now we have estimated the entering gases. So gases entering the oxidizing tower are ammonia, oxygen, nitrogen and H2O and NO. So these are the same compositions that were leaving the converter. Now the same components are entering into the oxidizing tower, and inside oxidizing tower only NO is reacting with O2 and giving NO2. And also it is given that 90% of the nitric oxide entering the oxidizing tower is converted to nitrogen peroxide. So we will rewrite the equation, then further we will write the amount of NO reacted, because these are the gas that is entering into the oxidizing tower, and out of these only NO and O2 they will react, and only 90% of NO is reacting, or we can say it's oxidizing. So amount of NO is 3.525. So 90% of this will react. So we can find NO reacted equal to 90% of total. So this is the amount of NO reacted. So now we can write the amount of NO unreacted equal to total amount of NO minus reacted. So this is the amount of unreacted NO. Now corresponding to this reacted amount of NO, we can find out the reacted amount of oxygen. So from this equation we can write 2 mole of NO combines with 1 mole of O2, and 3.172 mole NO is getting reacted. So corresponding to this we need to find the amount of oxygen reacted. So corresponding to this amount, we will get 1.586 kilomole of O2. So this is the amount of oxygen reacted, and the total amount of oxygen is 5.547. So remaining amount will come out as unreacted oxygen. So we can write oxygen reacted equal to 1.586 and oxygen unreacted can be estimated, that is 3.961. And we can also find out the amount of NO2 produced during this reaction. So here 2 mole of NO requires 2 mole of NO2. So the same moles of NO, that is 3.172, will produce same moles of NO. So NO2 produced will be equal to 3.172 kilomole. Now we can write the gases leaving the oxidizer. So these are the gases which will leave this oxidizer. So NH3 will come out as it is, water will come out as it is, nitrogen will come out as it is, and in oxygen unreacted amount of oxygen will come out, unreacted amount of NO will come out, and NO2 produced will come out. So here we can write the unreacted amount of NO, unreacted amount of O2 and NO2 produced. So these are the gases which will leave the converter. Now further, the leaving gas will enter into the cooling tower. So in cooling tower, already water is entering at the rate of 50 kg per hour, and in cooling tower NO2 is absorbed, and this NO2 is reacting with water and giving HNO3 plus NO. So we will rewrite the gases leaving the oxidizer, because the gases leaving the oxidizer will enter into the cooling tower. So these are the gases which are leaving the oxidizer, or we can say that these gases will enter into the cooling tower. And in cooling tower, NO2 is absorbed, or NO2 is reacting with water. So here this is NO2. So this NO2 will react with water, and nothing will happen to the remaining components, but only we have to pay attention that here NO2 is combining with water. So water is coming from this stream, that is 50 kg per hour, and also the entering gases. So these are the entering gases. These gases also contains the amount of water, that is 5.287 kilomole. So in cooling tower we will take basis as 1 hour. Then we will find out the moles of water that is coming from this stream. So weight is given, that is 50 kg. So 50 kg divided by molecular weight of water. So total moles of water entering cooling tower will be equal to, so number of moles is coming from this stream, as well as some amount of water is coming from this stream. So that is 5.287 kilomole. So total moles of water entering into cooling tower will become equal to 8.065 kilomole. Now, as per this reaction, we can say that 3 moles of NO2 produces 2 mole of HNO3, and the available mole of NO2 is 3.172 kilomole. So corresponding to 3.172, we can find out the moles of HNO3 produced. So moles of HNO3 produced will be equal to 2.115 kilomole. Now we can write the molecular weight of HNO3, and from molecular weight and number of moles we can find out the weight of HNO3. So weight of HNO3 produced equal to its molecular weight into number of moles. So it will become equal to 133.25 kg. Now we can find out that 3 moles of NO2 combines with 1 mole of water. So 1 mole will combine with 1 by 3, and the available amount of NO2 is 3.172. So it will combine with 1.057 kilomole of water, and the total moles of water is 8.065. So out of 8.065 kilomole, only 1.057 kilomole will combine with NO2. So we can write moles of water consumed will be equal to 1.057 kilomole. So remaining moles of water can be written as total moles minus consumed. So it will be equal to 7.008 kilomole. So in this side we will get HNO3 as well as the remaining water. So we can find out the weight of remaining water. So it will be equal to 126.144 kg. So we will get a mixture of HNO3 and water, because complete water is not reacting. Only portion of water is reacting. So HNO3 will come along with water. So total weight of acid will be equal to HNO3 plus water. So we can find out the weight percentage of HNO3 will be equal to weight of pure HNO3 divided by total weight. So this is the total weight and this is the weight of pure HNO3. So weight percentage of HNO3 will come out as 51.37%.